This video is for lesson 4.5, graphs of other trig functions. We studied in depth the sine curve and the cosine curve in section 4.4, but now we can use the same techniques to graph the tangent curve as well as the reciprocal functions cosecant, secant, and cotangent. So in a little bit, we'll spend some time focusing on each of those four trigonometric functions. But first, to get just a rough idea of what they look like, I'm going to have us turn back to a set of graphs you did a little while ago. So before we started section 4, you were handed a packet of graphs, or it was in your note packet, where you were asked to plot every 15 degrees for each of the 6 trig functions. Now, if you didn't get a chance to finish graphing the tangent, the cotangent, cosecant, and secant, maybe pause the video and do that now. But we'll just take a couple of minutes as you're coming back here to quickly discuss some of those characteristics. The tangent curve is a very interesting curve. We still call it a periodic trig function because it is repeating sort of an idea of a cycle consistently over our domain. Now, what I want to talk about with the tangent function, or at least look at a little bit more in depth, is this interesting characteristic we see at 90 degrees, or pi over 2, and at 270 degrees, or 3 pi over 2. Those vertical dotted lines are called asymptotes. If you had a chance to study the exponential functions, rational functions, and things like that in your algebra class last year, you would have been introduced to this idea of an asymptote probably for the first time. But an asymptote is essentially characterizing the behavior of the graph. So if we focus on this first chunk, or at least this chunk of the graph on the tangent curve, that sort of yellow chunk I'm coloring over, we would kind of talk about this idea of an end behavior here. We wouldn't necessarily call it end behavior because this is a periodic function, but we can still characterize the behavior of the graph. We would say, as x approaches 90 degrees, f of x, or the tangent of x, is approaching infinity. Okay? Asymptotes help us see this idea of infinite behavior. So as you think about walking on this curve, an asymptote, the way I like to describe it to students for the first time, is that it's an imaginary wall, okay? It's not actually there, it's not actually a physical part of our function, but it is there because our actual function, that gold portion that I've got traced over top of, is approaching that invisible wall, or that invisible vertical line. It's telling us that x will never be equal to 90, but everything in this case, everything to the left. Okay, so our function is approaching that y value, or excuse me, that x value of 90 degrees, or pi over 2 radians, but it's never going to be exactly equal to it. So again, infinitely close to, but never touching or intersecting. So hopefully asymptotes, hopefully that's not the first time you've ever seen that before. We'll talk more about them as we continue talking about the rest of these functions. And then if you're joining us for AP Calculus next year, we'll get a chance to kind of come back to that idea as well. So the tangent function, an interesting function. You'll notice I also have on the screen here ready to kind of project and show the unit circle. So I want to talk about those asymptotes and why those asymptotes are there. You'll notice there's a pattern, right? 90 degrees, 270 degrees. That pattern, if you looked at further values, you're going to notice that pattern continues. There's a difference there of 180 degrees, or pi radians. And so if you were to continue on past this particular graph, we would know the next asymptote would be at 450 degrees and so on. So we can say that the asymptotes happen at the intervals, or at the values pi over 2 plus n pi, where n is in the set of integers. Okay. Domain and range. Domain, this is an interesting one. The domain can be all real numbers except for those values at the asymptotes. You'll notice x cannot equal pi over 2 plus n pi, where n is in the set of integers. Again, if you've never seen that notation before here, this n, I think it's called epsilon. Like I said in class the other day, I'm not very good at remembering my Greek letters or the names of them, but this sort of kind of like an E or a C with a line through it, that is a Greek symbol, and that means in the set of, okay? Range, negative infinity to infinity. These functions, no matter what period or section you're looking at, they decrease and increase wherever. Zeros happen in a pattern. We see one at 0, we see the one at 180, we see another one at 360, and so on. So to talk about all those zeros, they would just be at every n pi. And then we're going to notice 1 period is pi units. So this is probably the best section to look at there. Okay, 1 period is going to be that curve that you see in gold or pink. Okay, from 90 to 270, that is what we would say is 1 cycle. Now, as I started talking and then moved on, this unit circle is here for a reason. Let's look at those asymptote values and try to understand a little bit better why they're asymptotes. So think about the tangent function in the unit circle, okay? Focusing on pi over 2 or 90 degrees and 3 pi over 2 or 270 degrees. Now we know the tangent is defined as the opposite side divided by the hypotenuse, or sorry, the opposite side divided by the adjacent side. It's defined as the y over the x. So knowing what we now know from the first half of chapter 4, we could figure out the tangent values for every single one of these. And this is something that you're more than welcome to put onto that formula card of yours. But we know if we were to find the tangent of pi over 6, we would have to take the y, which is 1/2, and divide it by the x, which is the square root of 3 over 2. So then we would have really 1/2 times the reciprocal of 2 over the square root of 3. Our 2's would cancel. We have 1 over the square root of 3, and we would want to rationalize that. So this is going to be the square root of 3 over 3. So if that's something you want to add to your unit circle, I know you know how to simplify fractions. So again, if that's something you want to just go ahead and add, then be my guest and do that. So then pi over 4, right, the y divided by the x, that's just going to be 1. The y divided by the x at pi over 3 is going to be the square root of 3, and then I'm going to stop and pause at the pi over 2. If I take the y divided by the x, that's 1 over 0. That is indeterminate form. We don't know what that is. That doesn't exist. So that's precisely why there's asymptotes at those values. We cannot evaluate that tangent. Likewise, at 3 pi over 2, we're seeing the same thing. Negative 1 over 0 cannot evaluate. Okay, so that's again precisely why we would say there's asymptotes at those values. Okay, so then quickly, the cotangent, or the rest of the reciprocal functions, you'll notice on this graph, as I've provided for you, I graphed the tangent in pencil so that we could compare the cotangent. So just like we compared the sine and the cosine, they're called sinusoids. They are transformations of one another. They're essentially the same graph, they just have been shifted left or right. The same is true for the tangent and the cotangent, but really we say that the cotangent is both a reflection as well as a horizontal translation. So it was reflected over the y-axis, and it was translated or moved left or right. Okay. Take a look at the domain, the range, the asymptotes, the zeros, the period. We could talk about those in depth, but Good to just take a look at those. Okay, and then the last two we like to talk about at the same time, and you'll see why as well, or you already know why perhaps, the cosecant. Okay, you'll notice I have its reciprocal function graphed at the same time. And if we described the tangent and cotangent as being reflections and translations, we can kind of sort of use that same description here as well. The sine function and then the cosecant function, you'll notice these are some interesting points that they share in common. They have asymptotes at every n pi, where n is in the set of integers. Okay, and the secant function. You'll notice it looks the same as the cosecant function. It's just a horizontal shift. It moved left or right. So we think about taking your cosecant function and taking that curve and moving it to the left, we can create that secant curve. So again, take a look at those characteristics. Noticing here that the cosecant and secant, neither one of them have zeros. Neither one of them will cross the x-axis, which tells us that y can't be 0. Okay, so then this video is going to take a look at essentially how do you graph these without the use of technology, without the use of a graphing calculator. And that topic, if I pause there, it's really important to me, but it's also really important to your understanding in general. My analogy is teaching my daughter to add for the first time. If I hand her a calculator, perhaps I've said this before, but if I hand her a calculator and say, here, type this number and this symbol and this number, and boom, you have your answer, she's not really going to understand what it is she's doing, especially if that's the first way she learns about addition or multiplication or whatever. So understanding these characteristics of these graphs and being able to graph them on your own is going to, like I said, aid your understanding much more than if I were just to say, here's the calculator, graph it, and be done. Now, working with the technology, of course, has its benefits and has additional aspects to your understanding as well, or adds to your understanding as well, but again, this is just that philosophy that we're going to start with. I should also say this section is kind of surface level understanding of these functions in a graphical sense. So we're not going to go that deep with them, but at least in this class, you're going to get some experience so that later on, if you're choosing to pursue a career or a course of study that involves more upper level math classes, you're going to have some experience to fall back on. So looking in your notes, you notice properties of the tangent function. Kind of already talked about those already. Feel free to read those. You might notice the end behavior actually uses some calculus in there, talking about limits, talking about behaviors of functions. Okay, so what are kind of the basics of that tangent function? Well, we know the period of any tangent function is going to be pi over the absolute value of b. Much like we saw in the sinusoids, to find the period, we took 2 pi and divided by that b value we saw. Okay. Your functions, you can still think of them in that same transformation manner. So we had in the past a times the sine or the cosine. Now it's going to be a times the tangent of bx plus c plus d. Okay. Some of these transformations don't apply exactly the same, but yet we could still understand them to some capacity. Okay, so if the period of our parent function is pi, then it makes sense that this b value is going to affect the period, hence that division. Okay. the vertical asymptotes, that's really the biggest characteristic of these functions that we're going to work on finding and then therefore using to graph. So to find the vertical asymptotes, you're going to take a look at the asymptotes of our parent function. So you're looking at the two green highlighted sections in that graph. You notice the first one's at negative pi over 2, the second one's at pi over 2, and then every other pi, or every pi over 2. So finding the vertical asymptote is just a simple calculation. Take your bx plus c and set it equal to pi over 2 as your comparison. Find x. Then take your bx plus c and set it equal to positive pi over 2 and find x. So let's try that with one quick example. Locate the vertical asymptotes and then quickly sketch the graph. Okay, we notice there's no other transformations in here except for this b value, right? This b value is affecting the period. It's affecting how wide or how skinny horizontally our graph is. So simple calculation, our bx plus c is just the x over 3. Recognizing that b here is actually equal to 1/3. Okay, so maybe I'll make a list of that first. Thinking about that tangent function, a tangent of bx plus c plus d. Okay, in this particular graph, the a is 1, the b is 1/3, the c is 0, and the d is 0. Okay, so if we want to find those vertical asymptotes again, take that bx plus c, which is just x over 3, and set it equal to your negative pi over 2 and your pi over 2. And solve. Multiply both sides by 3, we're going to get negative 3 pi over 2, and we're going to get positive 3 pi over 2. And now we can go ahead and graph it. So I know that there exists a vertical asymptote at negative 3 pi over 2. And at positive 3 pi over 2. Okay, here's where we get into memory, okay? We're going to memorize the fact that our tangent function is increasing from the left to the right. I know that it's going to, since the amplitude is 1 and the vertical shift is 0, it's going to pass through the origin just like my parent function. And again, it's going to rise from the left to the right. It's always what it's going to look like if there's no reflection and your other transformations have been unchanged. Okay, memorize the fact that it is increasing from left to right. So what would happen with something like number 2? Okay, number 2 is just a slightly different equation. We have the negative tangent of x over 4. So we could list all of our values. We know that our a is 1, our b is 1/4, our c is 0, our d is 0. But we notice that there is a reflection. Okay, so this graph has been reflected over the x-axis. Okay, so same thing, I can take my bx plus c and set it equal to your two chunks, your negative pi over 2 and your pi over 2. Multiply both sides by 4. We're going to get negative 4 pi over 2, which is the same as negative 2 pi, and positive 2 pi. Because there is no vertical shift, because the amplitude is not changed, And it's more so because of the vertical shift. I know that this function is going to cross through the origin just like its parent function, but because it has been reflected, it is going to decrease as we go from left to right. So notice it's just going to flip the other way. Okay, let's try a couple more, a little bit more involved or more going on in the equations. So number 3, locate the vertical asymptotes and sketch the graph. So same idea, take your bx plus c, which is x plus pi over 2, and set it equal to your two values. Again, that's something essentially you're just going to have to memorize since we're kind of just scratching the surface of understanding these functions. So solve. So subtract pi over 2 from both sides. With the first one, we get negative 2 pi over 2, which is just negative pi. And then we get 0. So we'll go ahead and sketch this. 0 and pi, negative pi, I should say. There still is no vertical shift on this one, and so I know I'm going to cross on the x-axis right in the middle of this. So this is the first time we get to see that it's not actually going through the origin because of that phase shift going on. And then secondly, we have another reflection with this one, and so it's going to decrease from left to right. So notice I'm not really paying attention to the magnitude of my curve. In fact, that green one was kind of poorly drawn anyway. But that's where we're not going to spend a ton of time talking about what that actually is going to look like. But we can get a rough idea or a sketch of what's going on. Now, if you were asked to describe what's going on in these graphs, you can still use the same language that we used back with sinusoids. Horizontal stretch or compress, vertical stretch or compress, horizontal shift, left or right. Okay, so a couple examples about the tangent. Let's take a look at the cotangent. Okay, the cotangent in comparison to the tangent function is simply a reflection as well as a reflection as well as a translation. So here, the period is still pi. To find the period of any function, you're going to be taking pi divided by the absolute value of b. Okay, then the values that we use for our vertical asymptotes, we're going to use this first chunk from the y-axis. So you're going to use the asymptotes from 0 to pi to find your vertical asymptotes. So vertical asymptotes exist where, I'm going to see how I wrote this, yep, where bx plus c is equal to 0, as well as where bx plus c is equal to pi. Let's try a couple examples there. Number 5, locate the vertical asymptotes and sketch the graph. Cotangent, my bx plus c is just a 2x, so set that equal to 0. We see that x is going to be 0. Secondly, set your 2x equal to pi. Our second vertical asymptote is going to be at the x value of pi over 2. Now, graphing the cotangent is going to be very similar to the tangent. What you need to remember about the cotangent is that it decreases It is a decreasing function from left to right. Maybe I'll go back to my tangents there and make that note. This is an increasing function. Cotangent is a decreasing function. So as I graph those values, right, or those asymptotes, 0 and then pi over 2, I know that because there's no vertical shift, there's no d value here, d is still 0. My function is going to have that kind of midpoint on the x-axis, and then again it's cotangent, so it's going to decrease. So start on the left high and fall to the right. Okay, a second example. Here we get a chance to, for the first time, see what's happening with this idea of an amplitude of something other than 1. Okay, and this one I might turn to the graphing calculators to show it a little bit more precisely for you. But we'd still go about this in the same way, right? This is the same function in that the bx plus c is the same as it was in number 5, so we already know the vertical asymptotes from that. So how is this any different? Okay, well, what we know about amplitude is that that is stretching or shrinking the graph vertically. And so if we have 1/2 times the graph, we know that the graph is getting squished or compressed. Like I said, I can sure plot this, but if you were to plot this graph all on its own, we don't have this one to compare it to, you would plot it the same as we did above, right? You would go grab your vertical asymptotes at 0 and pi over 2. We know it's cotangent, so it's decreasing, and it's going to look like this, right? All on its own, that's what it is. But again, what I'm going to do here is compare it to this number 5, and to show you that, I'm going to turn to my calculator. Okay, now first and foremost, when we're graphing on our calculators, we only have the sine, cosine, and tangents, as well as their inverses. We do not have their reciprocals. So if you're trying to type the cosecant, for example, you need to do 1 divided by the sine of x. Okay, there is your cosecant. The cosecant is the reciprocal of the sine, or it's 1 over sine. So in our graph, we're doing the cotangent, so I have to do 1 over the tangent of this 2x. Okay. At the same time, I am going to graph number 6, which is 1/2. I'm just going to use 0.5 times the cotangent, or 0.5 divided by the tangent of 2x, and we're going to compare these. Okay. Let's see if this allows me to change colors. Awesome. Okay, before I hit the graph button, I'm going to show you a trick. It's a zoom setting. It's a really nice setting to use, especially if you're graphing lots of trig functions. So if you press the zoom button, middle key under the screen, and then you look at number 7, notice it says zoom trig or z trig, whatever your calculator is saying. This is my app, obviously, on my iPad. I hate this thing, but it works. So if you press zoom 7, this is your trig window snap, and what's going to happen, you can look in the window settings then, is it's going from approximately negative 2 pi, negative 6.15, to positive 2 pi, and then setting your y min and max to negative 4 and 4. So that's generally a pretty good window. You can do zoom 7 and then change your window from there to see it, but there you be. So the blue function is number 5, just the cotangent of 2x. The pink function is 1/2 the cotangent of 2x. So what you notice, if you were to take the blue function and put the top and bottom of your calculator screen between your palms and squeeze your hands together, you're squishing that blue function, it's going to look like the pink. Okay, if we exaggerate this a little bit, I'll use green on the graph. If we exaggerate this, so maybe it's a number smaller than a half yet bigger than 0. So I want to have a reflection in there. If we did like, let's try to exaggerate it quite a bit. Like what would happen if I did 0.0005 times the cotangent of 2x? Watch what happens with this. That's a little bit too much. Okay, let me try that again. Let's maybe get rid of a couple zeros because I exaggerated it too much to see a good picture, or this calculator is just not going to let me show you. There, okay, that's effective. So notice that exaggerating that multiplier, that factor that we are squishing it by, okay, now it's getting 5/100th the size that it was. We've squished it so much more. So that cotangent curve, that middle kind of snake part of the graph is flattening out because we're squishing or compressing it vertically. So hopefully that was a good view to kind of compare and see how that amplitude is changing within our trig functions or within our cotangents and tangents. Okay, so on to the last two, the cosecant and the secant. We like to talk about these at the same time, just like we do the sine and the cosine, because they are just phase shifts of one another, okay? So the period for both the secant and the cosecant is 2 pi. So when finding the period of any of these trig functions, you're going to do just like you did for the sine and cosine curves. You're going to take 2 pi divided by the absolute value of b. Okay, to find the vertical asymptotes, you are going to use, I'm going to try to kind of highlight the sections. In the cosecant curve, you're going to use 0 and pi over 2. So you're using kind of this middle section of the graph. So you're going to take that bx plus c, set it equal to 0 to find your first asymptote. Take your bx plus c, set it equal to 2 pi to find your second asymptote. Now we can't use those same asymptote values for the secant curve because the secant function or curve is a phase shift. It moved to the left pi over 2 units. So we're going to use negative pi over 2 and 3 pi over 2. We're looking at this section of the graph. Okay, notice in each of those sections, if you think about trying to memorize like how to draw this, you're noticing they both, usually how I describe it is I say they both start high on the left. So we'll get into that as we look at a couple examples. Okay, so number 7, locate the vertical asymptotes and sketch the graph of y equals the negative secant of 2x. So vertical asymptotes, easier calculation. Because it's secant, we're going to set that bx plus c, which is just 2x, equal first to negative pi over 2, and then equal to positive 3 pi over 2. Okay, divide both sides by 2. We get negative pi over 2 divided by 2 or times 1/2, thinking about multiplying by the reciprocal. So we get negative pi over 4. Here, recognizing those same steps, we're going to get positive 3 pi over 4. Okay, so recognize that this represents a full period, and one period of your cosecant or secant curve, notice, includes 2 parabola-like chunks, right? Two U-shaped chunks. And so you actually have to split that interval in half to find your third asymptote. So negative pi over 4 and 3 pi over 4, directly in the middle of that would be pi over 4. So you've got a third asymptote, this third middle asymptote between or in the middle of the period. Okay, I know since my amplitude is 1, I make a note of that. Since the amplitude is 1, I know that the maximum and minimum values are going to be at 1 and negative 1 on my y-axis. So here we get to talk about that amplitude. Furthermore, this one also has a reflection. So if this were a positive secant, we would draw high on the left and low on the right. But because it's a reflection, it's going to be opposite of that. It's going to be low on the left and high on the right. Okay, let's try another one, number 8. Locate the vertical asymptotes and sketch the graph of cosecant of x plus pi over 3. And I'm actually going to change this one ever so slightly. I'm going to have us do 3 cosecant of x plus pi over 3. That way we can understand a little bit more about that idea of the amplitude it's going to do to the graph. So take your bx plus c, set it equal to, this is cosecant, so we're going to use 0 and 2 pi, and solve. First asymptote is going to be negative pi over 3. Second asymptote, maybe you need to do a little work for this. Think about 2 pi over 1. Get it common denominators there to complete the fractions or the operations with the fractions. That's really going to be 6 pi, show it like this, 6 pi over 3. And so 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. So pi over 3's. 2, 3 pi over 3 are pi. 4 pi over 3, 5 pi over 3. Okay, those are my 2 outer asymptotes. So split that interval in half to find your inner, right? So that's going to be at 2 pi over 3. Now, because this is cosecant, it's going to start high on the left, and I'm actually just going to sketch that, and then we'll fill in some values. It's going to be high on the left and low on the right. What I'm kind of trying to do is to ensure that the distance from my maximum to the x-axis is roughly the same. It doesn't need to be perfect. This is just a sketch. But here's where the amplitude comes into play. Those maximum and minimum values occur at that amplitude. So this y value, where that minimum is, would be positive 3. And this maximum would be negative 3. That is how the amplitude is being coming into play or affecting our graphs. It's just going to slide the graphs further apart. Again, that vertical stretch or compress. In this sense, it would be called a vertical stretch by a factor of 3. The amplitude went from 3, or those maximum and minimum values went from 1 to 3. Okay, so just trying to summarize a little bit, at least what you essentially have to memorize. You have to memorize those vertical asymptotes. You need to know how to calculate those vertical asymptotes. So the cosecant is at 0 and 2 pi. The secant is negative pi over 2 and 3 pi over 2. Okay, memorize that both of them, you're going to start high on the left and low on the right, as I kind of described them. Tangent and cotangent, similar manner. Memorize that the cotangent, you'll find those asymptotes by using 0 and pi. It decreases from left to right. Cotangent, it increases from left to right, and you're using negative pi over 2 and pi over 2 to find those vertical asymptotes. Recognize with all these graphs you saw in this video that you've only graphed one period of each of them. So taking a look at those distances, you can always replicate more periods either to the left or to the right. All right, thanks.